outside people?
We have the list here of people. So we have 29 people outside.
Excellent. Okay, so very good. First of all, it's very nice to see the people who I see in the room. And I can see here on a screen on the side that there are quite a few people connected remotely. So I think this is also good. And I have to say, I might be wrong, this seems to be a quite well attended codec workshop.
Yes, we have quite a few external participants.
In total.
And some couldn't get their mission approved. So
okay. Okay. So we have to work on that in the future and try to help start earlier is usually not for us, but globally. Okay, so this is the 9th codec workshop. I just give you a very quick overview. So we have on the site, I'm not going to just read out all the details here. On the site, we have 3 vacuum vessel sectors delivered. We have many hundreds of thousands of components delivered. For diagnostics alone, we have more than 100,000 components delivered. Okay, but for the big stuff like the vacuum vessel sectors, we have 3 sectors delivered. We have other items like the magnets. Pretty much all the magnets are on site now. We have the thermal shield on site. We have, of course, you will have heard, we've had some issues, and these issues are getting solved. I don't think if you're going on a tour, you'll be able to see, but there is a workshop where they are fixing the problems. As far as I can see, they're moving quite quickly. I think now my thinking this morning when I was up early, I was thinking we should not be focusing too much about energy on those things because there's a lot of energy on those things already. We need to focus on the things that we are not focusing on or others are not focusing on them because we will have plenty issues ourselves. So we need to keep our focus on our stuff and make sure we do our bit. Okay, I've worked in many projects and very often when I was in deep trouble in projects, everybody was going around talking about my problems and everywhere. And then suddenly I got my problem solved and suddenly all these guys were not ready. So we have to avoid us falling into that trap. So let's keep our focus on our issues. It doesn't mean I don't care about the other issues. It means that what I really mean is that there are plenty others worrying about them and we can't really influence them too much. So here you can see the ports plus the gray bit are the in-vessel diagnostics pretty much mostly. So this is kind of a picture of all the diagnostics. And this here is a picture of the magnetic coils on the machine, okay? This go on the outside and the inside. And actually, the picture on the right is almost populated. So if you do see one of the sectors, you should actually be able to see these coils and the wires from those coils. So it's not any more theory for diagnostics. We have more than 100,000 components delivered, and we have probably 20,000 installed. But it's a huge site, so seeing them all is not always so easy, okay? So you can see the little coils are small, so when you put them on the machine. Then yesterday we were having a chat about the plant and the tokamak, and the tokamak's over here. But actually, there's a lot more to building a plant than the tokamak part. You have a large infrastructure behind it, and you know this meeting really comes to its own on this whole region out here. Just B, C, D, where we are connecting wires, we're connecting cables, we're going back to codec, and we need data. Okay, and of all the tokamaks that ever existed in the world, I think ITER is a bit special because diagnostics are they can often be added easily enough to tokamaks, but it's not that easy to add them to ITER because you have a lot of shielding. Every time you try to do something, you got to go through 3 meters of shielding. So it's really important in ITER that we have a proper planning from the beginning and make sure we push on as much as we can. We may have to prioritize, we will prioritize how we implement things. As we have a lot of ports, as you see, we have a lot of diagnostics in the ports. And so far we've been doing a scenario whereby we've been sort of implementing everything at the same time. We've been running in a kind of a parallel mode. And relatively soon, we're going to have to go into a parallel mode, but fewer items in parallel. So imagine we're like an army and we're going through open countryside. And so we were able to move quite quickly. But now suddenly we have to go through a canyon. So we have to go and group up into groups of say 4 or 5. So we will probably start working, not in all ports at the same time, but in 4 or 5 ports at the same time. And then we try to get those finished. And anything that's in those ports, we try to get finished. Okay? From the INC part, you still have a bit of freedom, but at the same time, I think we need to start finishing things, because by finishing things, we give the world and our stakeholders a confidence that we get things done. Okay? What we don't want to have is everything to 90% and nobody thinks we have achieved anything. We'd be better off to have 40% of our equipment at 100% and then 30% of it at 70%, and then whatever is left at 40%. Then we have something to show for our work. So this here is a port plug structure. We have an assembly line of ports right now. You can see here the bit on the left is a part of the equatorial port, and the bit on the right is a part of it. And very soon the two bits will be joined together. And we have bought all the steel for these ports. This is the installation. Sorry, it's a bit dark. This is the installation in the building. So on the top you can see the pipes. These pipes are for one of the diagnostic systems. And it says here for the density measurement. So it's the tip, I believe. The tip or the dip. Okay? And the plastic is not just because we've gone cheap. It's because these pipes need to be connected together with some specific component. And at the moment, it's not there. And so they've just put a cover over it to stop the dust and the flies going inside. Okay? But this stuff is all installed. And there are thousands of bits installed, more like this. I just wanted to put in this morning just a small slide on the safety components, because ITER is a nuclear facility. It's the first nuclear fusion facility in the world. We don't have much TIC diagnostics, but we have a lot of SIC components of diagnostics. And many of our measurements have safety-related properties, okay? So I just wanted to highlight that we have a lot of safety-relevant components. You can see here it's over 5,000, and we still haven't identified all the components. So we're working on it. For keeping the regulator on board, it is really important that we show that we know where every safety component is, and we show that we are designing it to the right standards. So if you have safety components, please pay close attention to them. Make sure they're on your diagrams. Make sure you know what they're doing, and make sure that we're respecting them, because the regulator can come at any time, and they do regularly, and they will say, oh, PVS 55, you're working on the tip, you've got these big components, show me how you're managing it. And they can then go to the supplier as well. They have rights to do that. Okay, then you can see here recently the power boards have been installed around the machine. I think it's about 80 power boards, and these power boards were being tested in Corbière, and this was just a picture of this. So there's a movement. I want to just share with you very briefly also about kind of a high level strategy we've been trying to adopt. So, and we have a schedule. We always have a schedule, but very often the schedule has got a lot of lines in it, and it's very hard for anybody to get a big picture of all the lines. So we basically created this installation strategy tree. So we're now in construction in diagnostics. So there's been a big reorganization here, and we've been moved to construction. It's not a big surprise, because we're already well into manufacturing in many items, and as I said, we have installed many components. So it's actually quite a natural step. And Vigo, DG Vigo, told me in 2017 or 18 that he thought we'd be moving to construction around 2023, and actually we did. Okay, so it's not a big surprise. But you can see here we have 5 areas that we're focusing on. We have the in-vessel, mostly hardware. We have the port plugs. We have the ISS and PCSS, which are the bits behind the port plugs. We have instrumentation, electronics, electrical components, and we have the building components, raised floors, all these things. What we want to do is we want to put a strategy on those so we can push them all. What I don't want to do is end up focusing so much on the port plugs, then we find out that we have another 3 years of work to do on the ISS and PCSS, and we could have been working on it already. So the idea is to have a multi-pronged approach. We can be more strong, let's say, if that's a correct sentence. Of course, operation is where we need to go to, but that really is when we consolidate everything. And you know, INC is everywhere here, because INC will be related to the ports, INC will be related to ISS and PCSS, it's related to the tokamak and everything. But this area here is all about coordinating the installation of cubicles and the wiring, because we were finding that we were getting blocked on wiring because the cubicle wasn't there, and then they couldn't put the wires in, and then the wires couldn't be put in, the cubicles couldn't be put in because the wires weren't there. And so we've decided now to put a focus on this, and we get these kind of items resolved. And so this is focusing. This is maybe a bit on the sidelines of this meeting, but we are putting a bit of effort into the synthetic data through the IMAS. And I think this is very important for the design of the diagnostics, and we should use this to demonstrate that our systems are doing what we expect them to do. So if you're writing code, depending on what side of the line you're on, we should really be using synthetic data to test your codes and demonstrate that your system is as good as it can be before we put it into the plant. What we don't want to do is put it onto the operation. We start having an ITER pulse, and then suddenly we spend 9 months debugging our software because we didn't really debug it when we could have debugged it. We have time now to do that. I stop now, okay? So many changes, I would say, in ITER. It's big effort in rebaselining and reorganizing. I would say it's the biggest reorganization since I've come here, and I'm becoming old here now. I would say, regardless of this, the big picture of diagnostics hasn't changed. We don't have first plasma anymore. We have now called AFP, but we had first plasma and PFPO1. What's really happened is first plasma has vanished, joined up with this, but the amount of extra time for diagnostics is not that much. We might get a year or two, but it's not massive, okay? We were already in trouble for PFPO1. So actually, it's not a case where we can all chill out and you know, take a year off. Really not. And some people think that. It's really not the case. We will end up being in trouble, okay? But we will have to prioritize. So diagnostic installation began in 2020. I remember very well. It was in the peak of the COVID. We installed our first components on the building during the COVID. In particular, in 22, 23, many systems have been installed. And I have to say, there are many other systems delivered. I would say the diagnostic building now has cubicles installed. It's not fully clean yet. And once it's cleaned up, probably early next year, we will put in what's called the raised floors, and we will start dividing up the different areas for diagnostics. So probably, with a bit of luck, the next time you come here, you'll be able to go and see wherever your diagnostic is going. You'll probably be able to see which room it's going to be in, with some sort of separators in the room. I would say this workshop is another important step on the path to the realization of diagnostics. And you know, you are it when it comes to INC for ITER. You know, the buck stops with the people in this meeting pretty much. So, you know, I think it needs you. You're a solid team. Keep pushing forward. Have confidence, okay? And I wish you a successful workshop. That's it. That's all. A very quiet end. Does anybody have a quick question? So I hand back to our chair. Who's our chair?
That's yeah. I don't.
Good morning, colleagues. I was asked to chair this meeting, so I don't have any particular welcome word for now. And we are already coming to the time of the first report, so maybe we can switch to the report of Nikita. So Nikita, please have your time.
Well, I think there is an issue with the Russian presentation because there's delay with the bus. So we maybe will start with the China presentation first.
Fine for me. Then Zhao Li, do we have Zhao Li connected?
Yes, I have connected the meeting. No problem. Can you hear
can
me?
present? Yes. Do you have right to present?
I have uploaded the document on IDM. Could you please open it?
Yes.
Thank you. Okay, shall I start? Good morning, everyone. I'm glad to present our INC worker on behalf of CNDA INC teams. Next slide, please. There are 4 diagnostics in scope of CNDA, including neutral flux monitor, diverter laminar problems, APP-12, and radio X-ray camera. Next slide, please. Next, I will introduce each project one by one. The first one is about NFM. Next slide, please. NFM diagnostics will measure the total neutral emission from for both of DD and DT plasma and provide the evaluation of fusion power. The right diagrams show the location of fission chambers. All the signal will be transmitted to building 74 diagnostic area. All of the INC copies are located in this area. Next page, please. Actually, NFM has 2 contracts. The first is NFM 7. PDR of NFM 7 was approved in 2014, almost 10 years ago. And for remaining NFMs, the PDR part 1 was approved, was conducted in 2021. The maturity evaluation for all NFM-INC was conducted in last year. Take NFM7 as an example. The diagram shows the signal chain. We can see the signal from fission chamber after preamplifiers and then sent to SPU for data creation and processing. The red diagrams is showing an NFM system layout on HL2A in SWIG. And we got the preliminary test result. As we can see, this is a short of typical test result. The neutral beam injection lasted about 500 milliseconds. The counting rate of neutral almost following the same treat as a power of NBI. As shown in this slide, we can see the progress of NFM electronics and INC. After INC maturity assessment, there's some work on the improvement of electronics function and INC design. We also had some EMC test and related test on HL2A or HL3. And we got a preliminary test result. Some documents have been approved after the assessment, and now we are preparing for the document prototype for the coming FDR. Next slide, please. About the challenge and the issues. As a safe developed device, SPU, signal process unit integration to CODAC, requires a lot of work. Especially the project delay also makes this work face many uncertainties. Another solution, prototype, has been established functionally test on the HLC device. The equipment of this solution is selected from IO product category. category to meet NFM requirements and may be better compatible with CODAC. We plan to visit I/O in November in next month, and we plan to discuss this topic with I/O colleagues. Next, please. About another diagnostic system, DOP. Next slide, please. Yes. Next. Thank you. Another diagnostic project, DOP, has a primary contribution to the measurement of the density and the temperature at the diverter target for advanced control. It's a very huge diagnostic system because it has almost 24 DOP NC copicals, up to 700 signal measurement, and provide 200 analog output as driving signal for DOP all-in-one power supplies. Next slide, please. All-in-one power supply is a key component to provide voltage for probe, which located in diverter. At this moment, we have two technical routes for DOP all-in-one power supply. Both of these two prototypes have been tested in HLC. The red picture shows the installation of copicals with power supply in our tokamak device. The following diagrams show the test result of power supply. As you can see, the test of technical route 2 with the isolation has a better performance. Next slide. Thank you. This diagram shows the progress of DOP NC after PDR. There's some work on the optimization of NC architecture and control operation development. The work focused on the reliability, confirmation of driving signal, and real-time data transmission. I will discuss these two topics in detail in next slide. And some documents have been approved after PDR, for example, the on-site test and commissioning plan and the concept of operation. The other documents are all under preparation for the coming FDR. About the challenge and the issues, the first one is about the AO signal reliability confirmation. Because NI PXI Express modular will provide the analog signal output to DOP-A all-in-one power supply as driving signal. But how to issue the accuracy of the AO signal during the discharge process? We want to know whether IO diagnostic systems have the similar requirements and effective solutions. The second question is about the offline post-processing data. Because DOP plan to provide the post-processing data of density and temperature, so we want to know, has CODAC published the data post-processing or analysis strategy? Maybe we need to have the further discussing with IO colleagues. Next slide, please. The third topic is about the project from SIPP. Next slide, please. Yes, it's about EPP12. This project is to provide a unified platform offering stable support, nuclear radiation shielding, and cooling or baking function for 6 Telnet systems. It comprises of 3 assemblies: PPS, ISS, and PCSS. Next slide, please. EPTL now is in the manufacturing phase. Series of MRR are prepared, and DSM machine is ongoing. The primary and tasks during this phase include the research and preparation for the level and mid cable installation in PPS, and the research preparation for the cable routing and installation in ISS and PCSS. Next slide, please. This slide shows the level and MI cable installation in PP. 3 distinct the 3 level unit and a total of 130 MI cable will be installed on our side. The initial plan for cable installation has been published. Next slide, please. This slide shows the cable installation in ISS and PCSS. The cable installation in ISS and PCS will be carried out by 2 teams. The one led by PI at SIPP, and the other one is by a contractor at the IL side. Currently, ANSI activities focus on the conduct a comprehensive assessment of the cable installation process and monitoring the process and update of relevant components provided by IO and by other PAS. About the challenge, as the port integrator, any design changes or delay in delivery from Tenet or from IO will bring the challenge for our integration. According to the plan, the level are scheduled for delivery by the end of 2024. The new design strategy for the electrical components in ISS will be completed by the end of this year. Next, please. About the lessons. Sorry. As a port integrator, our critical lesson learned is about the importance of communication. Only keeping a good communication and it ensure alignment in process tracking and updates and other related workers. Okay, next slide. It's about the last project, radio X-ray camera. Next slide. XC is designed to measure the plasma X-ray emission with higher spatial and temporal resolution. XC had its FDR in 2019, and our colleagues are preparing for the MR in this month. Next slide, please. This slide shows the progress of IXC. After FDR, there's some work on the stability development environment, and IXC completed the NDS program of COTS device. And they are working on the document preparation for the MRR. This slide shows the detail about the documentation. Sorry. The documentation includes the SMS, wiring corpus, and SPMP. And part of MR document, modification based on the IOCAP comments are ongoing. For example, the MIP, STP, and SADD. EA modular updating and slow controller development are also ongoing. Next slide, please. About general issues, my colleagues have discussed with IO about the PXI configuration, and we reserved the support document about this topic. And so the test is ongoing. And about the data process for the data, we have some problems on deco card. Firstly, we want to know how is the process program added into our INC programs, because the NDS and DAQX doesn't provide the interface for this worker. And how to obtain the value of configuration PVS in the processing programs. I think we need the further discussing with our colleagues about these topics. That's all for my presentation. Thank you.
Thank you very much for this presentation. Is there any question from the audience or any comments you want to share regarding the work done by Chinese DA?
Yes.
This is Mike Walsh again. I think it's a nice presentation. Thank you very much. Can you hear me?
Yes, Mike, I can hear you very clear.
Yeah, so nice presentation. I see you listed out a set of issues that you wanted to consider. You put them as kind of questions. If there's time in the meeting, I would suggest you harvest those comments and take the time to go through them and discuss them. Even if you don't do it in big groups, you might do it in smaller groups. But I think these points are valid points, and we should address them, and we shouldn't be embarrassed about them, whether it's IO or not IO. It doesn't matter. If IO is not stepping up, we have to know about it, and we should discuss it in an open and good way to try to improve and try to be better, okay? Because as I said at the beginning, we are it when it comes to INC in ITER diagnostics. This global team is more or less it, okay? So we need to fix things and do things better. One thing I forgot to mention this morning, I'm hijacking this now for a second, is that there's a big push now on this project to have teaming, have more one team sort of all working together in a kind of an integrated way. Now, for different people, it works differently, okay? But we can start by having a mindset of working together. So if something is wrong, don't think I'm going to blame A or I'm going to blame B. Think, how can we fix it? So try to get that mindset. Even for myself, it's actually helping me, because instead of seeing the problem, my mindset is more into seeing what's the solution. How do we fix this? How do we fix this? Oh, it's Arthur's fault. Okay, well, we don't care. It's a problem. We need to fix it. How do we fix it? So if we start with that mindset, we can then think about joining up forces. I mean, I see a lot of people here who are really good, who could help others around the world. And we should use that where it's possible. We don't want to see people finishing a job and going off doing something else and then having all that experience that we absolutely need lost. We should think, how can we work cross-function even if needed? It might sound a bit strange right now, but don't think that way, okay? Try and think, how can we use our skills to make it all fly? It doesn't all mean you all have to come to ITER. It doesn't. It means that we have to think, how can we work together? Even if it's not our scope immediately, we could think how to flex it around. So I'm hijacking your talk, so go.
No, that's a perfect point, and the goal of the workshop is to raise this issue. So all the issues that you are going to raise during your presentation, during the discussion, we will store them, and we will make action out of this workshop. And we will try to follow up within IO, but not only within IO. The idea is that we will get the expertise of everyone around the table to solve the issues and also to share the solutions. So the issue that have been reported by China, I'm pretty sure a lot of you will have the same exact issue. So it's we need to thank them to have detected early enough, and the solution will be shared by everyone.
Yes, I think it's a good chance for us to communicate with each other. Thank you.
those issues you put down, let's definitely harvest them. And if others have issues, let's harvest them as well.
Maybe I can add that in the previous workshops, at the end, we had developed a list of action items, what we need to work on. And these are exactly the kind of issues for which China has already proposed some solutions, which we need to compare and discuss. And this is an opportunity also considering that our development platform is Coda Core system, which has been optimized maybe for industrial systems, large number of channels, slow sampling, but not the high performance acquisition, especially image acquisition and processing. We need to come up with a proposal and guidance how to do this. Maybe a real-time framework is an option. Maybe some processing needs to be done in even GPUs, which we don't like so much because technology is changing all the time. And this way we have to compare this high performance computing and data acquisition and find some solutions. And also timing was mentioned because when timing is tested, normally it's tested on a small scale with one board, but not necessarily with the distribution to many boards and across many chassis. So this is also an important topic.
Morning, everyone. I have a question on slide 23. It's quite specific, but I was wondering if it's maybe also can Arthur follow up on the answer. So I see that the software architecture and design description is part of the MRR. So I'm not really familiar with the MRR of the INC, what it involves in terms of software architecture. But I'm curious if it's what kind of updates are typically done after FDR on the design description of the software. And in this case, and if it's normal to have an update on the MRR, because I'm not familiar with the scope of it.
So there will be a talk dedicated to that on this afternoon, the talk number 13, where I will explain just the transition from design to manufacturing. So the idea, I will present really what is expected at FDR, what is newly expected on MRR, and how we intend to follow the software development, which is not really the focus of the MRR, but there is a process for software development which is not fully binded to the hardware manufacturing. So I will have some slides for that this afternoon.
Thank you.
Any other questions? Do we have our next report, colleagues, Kim? Or we can. Nikita, you here? Maybe you can.
Hello, colleagues. I'm online today, and our presentation will be from Anton Nikolaev. He is on site in the room.
Oh, I suggest you can come here. It will be easier for you to put the slides. So is the slides on IDM or? On IDM. Okay, I will open it. I will open them. You can come here to present.
Hello, dear colleagues. My name is Anton Nikolaev, and I'm a member of Russian Domestic Agency INC team. And I would like to make a report on our technical progress and challenges that we have met in our experience. Russia takes part in development of different diagnostic systems as well as technological ones. All of them are on the different stage of their life cycle. The three technological systems have partial readiness: coil power supplies, gyrotrons, and PPTF. The INC diverter neutron flux monitor is going to the MRR stage after the FDR in 2022. Our NPA, PRIS, and VNC and diverter Thomson scattering are going to final design review stage. And the latest one is the high field site reflectometry are preparing for preliminary design review. Well, during our work, we encountered a number of problems, okay, but made a great progress with INC prototyping and project document development. Let's focus on the challenges that the developers viewed during systems prototyping. H-alpha system, for example, uses MXI rear devices that are already outdated and have to be changed to the latest. Also, they need scientific-grade cameras that meet all the requirements of radiation hardening. VNC system made a great progress with working with diamond detectors, but fission chambers part should be detailed in the future. Charge exchange recombination spectroscopy system needs to integrate the fiber bundle heating control according to the ITER requirements. The main problem that Gyrotrons control system has encountered is obsolescence. It is difficult to migrate from outdated of the equipment, Siemens controllers, timing models, and so on, or previous Codeco system versions to the latest one. It was not very well defined and easy way to make such a migration. The several systems that we already mentioned are developed by the contributors, but there are some projects that domestic agency does on its own. About 2 of them we are going to report. First of all, it's virtual neutron camera INC prototype. Well, to start with, let's make a brief overview of the VNC diagnostic INC. It consists of 2 subsystems, lower in lower port 14 and upper in upper port 18. The main plasma parameter that the system provides is neutron emission profile in real time. Except for that, it is also contributes to the calculation of some backup parameters that are described on the slide. The detector that are used for this is fission chambers and diamond detectors. They are placed into detector units, 2 diamond detectors and 2 fission chambers in each of them. The overall number of units is 12, 6 in upper subsystem and 6 in the lower one. The hardware architecture of data acquisition channels for the upper subsystem is presented on the slide. As you can see, detector units are connected to the preamplifier modules separately for fission chambers and diamond detectors. To transmit the signal over the diagnostic gallery, the fiber optic transmitters and receivers modules are used. As for control of the high voltage for the detectors, the Siemens controllers will be provided. For digital processing, we use NI equipment from the ITER fast controller catalog. As we already stated, our team developed the prototype of diamond detector acquisition channel. The main part of the prototype are presented on this slide. First of all, it's a CVD detector of different volumes. Then it goes 6-meter mineral insulted triaxial cable. And then we have 4 channel modules of signal amplifiers and transmitters with a power supply. Also, we have specially developed optic galvanic isolation line, which serves for noise reduction of the electrical path and consists of the transmitter module, the receiver module, and fiber optic line 50 meters long. For digital data processing, as we already mentioned, we use NI 5772 and NI Flex Rio boards that are connected to the fast controller with Coda core system. The main part for us of the digital signal processing is the LabVIEW FPGA code that implements the algorithm for diamond detector signal parameters calculation. Well, briefly, the code works as follows. We manually set amplitude threshold that is used to distinguish pulses from the noise. Then the signal goes through the baseline calculation, the median filtration, and then the peak values, count rate, and total number of pulses are calculated. Also, we calculate the integral or charge spectrum by summarizing the signal samples. Along with that, we provide the needed buffers for raw data transmitting and oscillograph mode processing. The host side view of the LabVIEW application is presented on the slide. Here we can see the 3 main windows: oscillograph mode, amplitude spectrum, and integral or charge spectrum. The overall architecture of the developed software is presented on the current slide. Firstly, it's device drivers for physical access, for example, NI Rio drivers for our FPGAs. It's special libraries that provides codec and some additional functionality. For example, DAN, SDN, NDS, and so on. Then we have NDS driver layer that is used for integration purpose of our devices. All of that built into Epic's input-output controller application with corresponding database files. To integrate the used hardware and the LabVIEW FPGA application, we use the standard codec core system resources. We developed the SDD project according to hardware that has been presented. The developed NDS drivers, data acquisition and data archiving network drivers are used for data acquisition from LabVIEW FPGA program, system monitoring, and transferring this data to Epic's IOC and transmission of raw data with the help of DAN IP. The drivers follow the three-way structure that are represented on the slide. We also carried out the DAN archiving testing. We use the recorded signal from waveform generator of finite duration with no number of pulses and transmitted through our digital processing units. We use the codec provided services like DAN IP monitor, DAN plotter, and other to check the archiving process. And for transmission to the dedicated server, we initialize the special configuration files and tested it. Here you can see the HMI screen that we developed and use in Codec Control System Studio software. We also included the screen with SOS implementation on it. We made the testing of the whole data acquisition channels. Here on the slide, you can see the whole prototype view. The next project we present is a 6-channel fission chamber single simulator for DNFM INC testing. The simulator is intended to check the functionality, test, and provide preliminary configuration of the DNFM diagnostic INC. So the DNFM diagnostic will measure the time resolved neutron emission from the ITER for both DT and DT plasma, providing the evaluation of the fusion power. The DNFM INC system consists of 3 subsystems which are located in lower ports 2, 8, and 14. Each subsystem processes the signal coming from 2 detector modules, which are composed of 3 section fission chambers with varying amount of fissional material. So every DNFM subsystem should perform independent calculation of measurement parameters using 6 signals from fission chambers of different sensitivity. Let's speak some about input data for simulation development. As I mentioned, DNFM subsystem will calculate 6 fission rates for 1 value of total neutron flux. On the basis of the calculated converting constants, the dependencies of the neutron flux of fission rate were plotted for each detector. Based on the 6 input count rate values, in compliance with the measurement procedure, the simulated neutron flux value shall be measured with INC. This slide demonstrates us the concept of testing the DNFM INC with simulator. Simulator connects to the prototype through the termination box and 6 differential signal lines. To use the simulator, first of all, you need to create a neutron flux test profile. Then you calculate fission chamber state profiles using converting constants. After that, you will be able to get output electric signal with necessary pulse rate values. After this signal processed by INC, you will get measured neutron flux profiles that should be the same as the input one. Simulator constitutes 3 identical PC-based devices. Each of them has built-in PCI Express waveform generator. The generator board has 2 independent channels with single-ended output, or can be configured as 1 channel with differential output. At the moment, we use 1 channel configuration of each board, so we have 3 channels provided differential signal. To make a 6-channel simulator, the single-ended to differential converter was designed. This approach will be tested in the nearest future. The synchronous operation of devices is provided on the hardware level by using triggered systems of each board. Also, some technical specifications for signal device are presented on the slide. Here you can see the preliminary user interface of the simulation software. It allows you to influence on the generation signal in various ways, providing pulse height distribution, length and time resolution of data inside the file, and so on. So to make a conclusion in our work, we can point out the main results with work that has been done by the domestic agency. First of all, the testing of the VNC data acquisition channel with diamond detectors was provided. It also included the testing of codec integration software and some of its services. The works are in progress right now. For example, we need to develop the fission chamber channel and so on. Also in the NFM-INC diagnostic system, it is important to create a multi-channel fission chamber simulator. It enables to perform testing without a real neutron generator and check all functionality of the system. Thank you for your attention, and I would be happy to answer your questions.
Thank you, Anton. Maybe I can make just a small comment before we come to questions. As a CRO of this system, I can say that it's maybe a bit underestimated the importance for, on the slide 6, it was just one primary measurement, but the diagnostic has two primary measurements for 13 and 14. And for the NFM, a small maybe comment that we didn't yet close FGR, so it's maybe a bit early to speak about MRR stage.
Okay.
Otherwise, that's what, thank you for this update. We can have some questions, so maybe we start with questions from the room. Do we have any questions here? Stefan, please.
What is your experience with LabVIEW FPGA for your analysis in terms of resources needed in the FPGA? Is it an efficient way to do it? And have you been able to do a modular design that later it is possible for someone else to make changes?
Can you repeat, please? I don't think I clearly understand the question.
Yeah, the question has two parts. Since you are using LabVIEW FPGA to analyze your pulses, the question is LabVIEW FPGA resource efficient? You need resources in the FPGA.
Yeah.
And if you would compare VHDL programming with LabVIEW FPGA programming, would you be able to minimize the resources needed in the project?
Maybe it's a good way to reduce the used resources, but I don't think we will do it because it's harder to make a VHDL program than LabVIEW. I think so.
Okay. Anyway, you have sufficient resources in your FPGA for what you are doing, as I understand.
Yeah.
There's no limitation.
I can add a little comment here. Can you hear me?
Yeah.
Yes, we don't yet perform HDL for programming for LabVIEW models, but our colleagues have from DNFM team have some experience with HDL programming with Xilinx native evaluation boards, but out of ITER final design models. And for the quantity of resources in DNFM system, as good example, with previous FPGA models 7966, we have almost we was very tight with FPGA ISOs and the size of matrix, and with 7679 it's okay. With new model 7976, excuse me, it's a lot of ISOs for our tasks and for signal processing. And as the second part of question is modularity of our firmware. Yes, with firmware is, for example, for VNK, it can be pretty quick change. It can be pretty quick change to some additional versions and some configurations for universal purpose.
Thank you.
I can ask further to this question. So it's mentioned the prototype with one channel, right? And there can be several channels implemented in one FPGA, and in your plan will put in several channels in the FPGA can also lead to the risk of insufficiency of the resources. That's the first part of the question. And second, when you do the testing, you have functional check of the FPGA work, and then you do the FPGA like routing and this process. Have you tried this algorithm in real time on the real FPGA, or you just functionally tested the algorithms? So these are two questions. It's curious to me.
For the first question, we will use the one FPGA to process the signal from two channels. And we, on the slide, where it was here, we tested the FPGA processing in the real time with the real diamond detectors and neutron generator signal. So it works in real time and quite good for our life cycle stage. So here we have the LabVIEW, Codeco system, and the optical isolation line. Okay, sorry. Here. So it works in real time right now.
Okay, thank you for your answer. Do we have any? Yeah, we have another question from the room, please.
So one of your slides mentioned about the SDD project.
Yeah.
Did you use
This one.
EA and the variables coming out of EA to import into SDD, and that's how you did the programming?
As I remember, we create the SDD project manually. Don't use the enterprise architect if you asked about it.
Okay. All right, thanks.
I think we are going to have some discussion about the EA to SDD tool. So the current status, it has been tested on several EA projects. The first tests were bad, so we were not. It was not possible to work. So the EA to SDD tool has been updated over and over. So there have been a lot of tests ongoing, and I think currently we have one example for the Q0. I think maybe Hervé will mention it, which was working. For a bit more complex system, there are still ongoing actions. So we need to make sure that the syntax, everything on the EA is matching the tool, and the tool has sufficient options to take. So it's not yet fully working, but in a very near future, I think we can consider we have a good tools that may have a few bugs here and there, but should be able to be used by everyone.
Thanks.
Any more? Yeah, please, one more question.
One more question. How this optical isolation module works? Do you send the analog signal or digital?
Yeah, it's a fully analog isolation line.
Okay, and have you tested the stability, how the parameters change with temperature or other parameters? How stable it is?
We don't make such a testing. Maybe our contributors, because we don't make it in the DA. So I don't have any results of the test right now, but I think it will be provided in the future.
Okay, so this is basically the amplitude modulation used, yes?
Yes.
Okay, thank you.
Thank you. Maybe we can give some space for the questions to those connected online. If somebody connected, please. If somebody has questions from those connected.
I can give two comments according to previous questions. First of all, in VNC system, in our plans, we want to try models with 4 channels for fission chambers with less frequency, but if it will be good, we will use it for diamond detectors too. So we will have 4 channels for one model, FPGA model, and in our experience, it will be enough resources in NPGA for it. And the second point about SDD project, we don't use input from EA project, but variables in SDD project are the same names and the same quantity as in our EA project, but both projects are not finalized yet. It's in development.
Thank you for your comment. That was very interesting to hear about diamonds, particularly because diamonds require high frequency of ADC to be used, to my understanding, and that can be even more challenging that for fission chamber to implement online algorithms here.
Yeah, now we use the ADC with 800 megahertz sample rate, and for fission chamber it will be used 250 megahertz. And we will test it for the
500.
500. My mistake. 500. Yeah.
And about the raw data, we assume it's an open question of the transferring it to the codec.
Yeah, we tested it for one channel. I think it will be a challenge to make such transfer for a lot of channels, but we will test in the future. We don't know.
My concern here that I know that with the low early discussed frequencies, we already have issue with a high amount of channels for VNC and for DNFM also. We already have a problem, not enough maybe connection points to codec here. And if we further increase frequency, I think it's needed to be well justified if we need it, because it can be even more challenging or impossible to transfer all this raw data to codec. So maybe we need to discuss it additionally later. Yeah, we have another question from room.
Yeah. I'm sorry, can you hear me? Yeah. That's a very good question about or point about the raw data. And I would argue, because we have several diagnostics, they're going to have the similar issue where we have an FPGA that's acting on high bandwidth, high speed data. Some doing like band pass sampling on RF or IF signals. And I would argue against trying to store raw data for a neutron measurement like this. I think if we put our time and effort into properly creating our firmware, our FPGA code, and benchmarking it, calibrating it, that we don't attempt to try to store the raw data. It kind of defeats the purpose of an FPGA in a certain sense, which is to crunch the data in real time and give a real time pre-processed finalized signal for later use. We do something similar on D3D. One thing what we do find useful is that we'll take snapshots of the raw data, for brief periods of time, so that we can always go back and check our algorithms to make sure that our algorithms, that after we post-process the data on a CPU, that we get the same results that the real-time FPGA is getting. But we only take brief snapshots, that what we can compare with, because trying to store, archive, transmit all this data at these kinds of sampling rates and the numbers of channels is going to be daunting. And actually on D3D, we find that the time that it takes to post-process the enormous amount of data, just transferring it back and forth from the database to a CPU to do the computing. At first the physicists wanted it, but after a while they realized it was just too much and they don't use it. So once we get our FPGA code working, and then we have the ability of capturing little snapshots that we can crunch later to prove that it's all working, I think that's sufficient.
I think that the key point is what's important is to be able to access them when we want, either in the beginning of when we do commissioning, or for whatever reason in the future, if we want to check anything, we need to have the ability to to store all the raw data if we have the needs for that. After storing all the time, all the raw data for all the diagnostic system, it would create a huge amount of data which will maybe never be used, most probably never be used. So that we understand fully the principle. So the message here is we should be able to do it. So we should not have a system for which we are stuck and have no access to the raw data, because that would be dramatic for future exploitation. But we really encourage to have these options to take snapshot or to decide for one pulse we want to have the raw data for this particular pulse for whatever reason we want in the future. So that's the freedom. We want to have this freedom in the future. But it's clear that the storing data for all diagnostic at all time, it's costly and for very small, very low use in the future.
Maybe I can add also here from our experience on JET. We have some cases when the raw data was not provided, and later it was complained that some setting was not optimal, but we cannot return time back, and the experiments are very costly itself, so that some physical data was lost, especially when we go from the low power experience to high power experience, and we have challenging like superimposed pulse separation cases which may be not fully tested, so that we have to be very careful here. At the same time, from the JET experience, we have the complaint when installing the system that there are no resources to transfer it, but in the course of year, like in 5 years, in 10 years, we were told that now we have this power to accept this data. So with the time it can be easy, and we're just trying to think of enabling this opportunity, at least for the moment, not to close the door from the beginning. Thanks. Do we have any? We have.
I have a quick question.
Yeah, please.
I'm surprised to hear that for acquiring diamonds you use 800 megahertz, because as far as I know, they are very narrow pulses. So how do you get features from these very narrow pulses, typically 1 nanosecond, 2 nanoseconds, to see the peak or something on this pulse? Unless you use a shaping amplifier before acquiring it. So I would like to know the details on it. Otherwise, you have to sample more than 800.
So as I mentioned, we use 800 megahertz sample rate for process the diamond detector signal. And in our experience, the diamond detectors give us the signal with the pulse width about 20 nanoseconds. 20.
After preamplifier.
After preamplifier, okay. I think raw data is the data after the conversion. And amplifier. Okay. Yeah.
I think raw data is data after ADC conversion when you after you digitized it. So raw data is not an electrical signal on a wire. But
okay, do we have, we have another questions in the room. We have time and we have questions.
Yes, I've got a question about the fusion chamber. Does the fusion chamber require the calibration to give a good result, good signals? And does the fusion chamber evolve in the time? I mean, when fission happened, so there is some degradation inside the fusion chamber, and does the signal stay the same all along the lifetime of the vessel?
I don't have answer to your question because I'm not a physicist. Okay, I'm the INC developer, and I really don't know.
Maybe I can comment a bit here. we have performance analysis documents which shows that due to the neutron irradiation of the uranium, we have plutonium formed inside. It's not huge amount, but it has much larger cross section, so the sensitivity rises for the fission chamber with the time. That's known effect, and to my memory, it's about 6% of the increase of the sensitivity for the whole lifetime of ITER, calculated for previous staged approach, of course.
Thank you.
I have another question myself also. We have difficulties. Have difficulties with the X-vessel triaxial cables. So it's known it's not in the catalog, and it's known that that cable presented in the catalog has not passed the some test of the manufacturer. So there are a couple alternative solutions were named. From my own side, it was something proposed, and I know that some military-grade cable was suggested from RFG side. Which of the cable used for simulate X-vessel triaxial cables in this case?
Colleagues, I think about this question we need to discuss it with technical coordinators from DNFM and VNC systems. For testing in our work, we use prototype cables from Russia.
Yeah, it's all.
Which cable can you repeat, please? From?
It's as I remember, it's with cables are prototypes without any final name for this time.
Okay. And maybe one more question here. We have a couple minutes more. It's discussed that it can be beneficial to develop together signals from VNC or data from VNC and the RNC system. Do you have any comments on the progress of analyzing this data together, your plans and visions update for us?
We have no update about this question. The nearest updates is the make multi-channel processing units, and for fission chambers. We don't work on the RNC and VNC data connecting.
Okay, we can have one maybe last question, if any, yeah, before break. If not, we can. Yeah, please.
It's not a question. It's just a point on the agenda, because this afternoon we are going to visit the INC lab in Corbière, and the plan is to use the personal cars to go there. So I would like to know if you could raise your hand if you don't have a car, so that we can organize the carpooling. So is there anyone who came by bus and needs a drive to go to Corbière? Raise a 1, 2, 3, 4, 5. Okay, so we will have plenty of cars, and we will organize just before going to lunch. We will discuss how to organize the trip, how to go there for the ones who have a car. So we'll maybe show it's not very complex, but we can go all together. That's the idea. So let's have a coffee break now.
Yeah, let's thank you also again, the reporter, for this good presentation. Thank you.
And we resume at 10:30.